Hey guys, welcome to GER Hub Mathematics and Statistics Lessons. Thank you for your subscriptions to the channel. Thank you for your likes and comments to our videos. Thank you for your shares of our videos. We are very grateful from the decks of GER Hub. If you haven't subscribed to the channel yet, please do that now by clicking the subscription button below. Please subscribe to the channel. Please subscribe to the channel by clicking the subscription button below and endeavor to turn on your notification bell or your notification button so as to get notifications on videos we shall be uploading subsequently on mathematics topics, statistics topics, as well as research project writing topics. Okay, it is very important you turn on your notification bell. Thank you very much. Now, in our previous lessons on probability theory, we had discussed random experiments and sample spaces. It was difficult or challenging to represent sample spaces theoretically, in the sense that we were always gambling or trying to know or determine or ascertain what outcome should or should not be in a sample space. So that was a major challenge in trying to represent the sample space for any given random experiment. Trying to determine what outcome should or should not be in the sample space was a major challenge. Now, the probability tree is one diagrammatic approach or a diagrammatic approach for overcoming this particular problem, and we shall be defining the probability tree in this video. So this video comes to address that problem, and that is why we shall be answering this question: what is a probability tree? Okay, so let's start with giving an answer to that question. A probability tree is a diagrammatic ordered representation of all the possible outcomes for any given random experiment with accompanying probabilities for each of the outcomes. Okay, so a probability tree is a diagrammatic ordered representation of all the possible outcomes for any given random experiment with accompanying probabilities for each of the outcomes. So let's take note of this word ordered. Okay, so the word ordered there tells you that the probability tree overcomes the demerit of theoretically representing sample spaces, because in theoretically representing sample spaces, you will notice that the problem we encountered was trying to ascertain what outcome should or should not be, what outcome is repeating itself and should not be in the sample space. So a probability tree is a diagrammatic ordered representation of all the possible outcomes for any given random experiment with accompanying probabilities for each outcome in the sample space. Now take note of this again, this statement I'm underlining. Take note of this statement. Now this was another thing that was absent in theoretically representing sample spaces. In representing sample spaces theoretically, there was no accommodation whatsoever for accompanying probabilities for each outcome in the sample space. So the probability tree takes care of this problem we encountered in theoretically representing the sample space. Now, let us now see what a probability tree can be very useful for. So let's say a probability tree is very useful in probability theory because, one, it represents or presents a sample space. It presents a sample space in a more elegant direct, and comprehensive manner. So this is one great use of the probability tree. It presents a sample space in a more elegant, direct, and comprehensive manner. This was one thing that was absent in using the theoretical representation of a sample space in our earlier videos. Okay, so using the probability tree ensures that there is some manner of elegance or beauty in your presentation of the sample space. Using the probability tree ensures also that it is very direct. In an ordered manner, you can get the outcomes that should be in the sample space. Using the probability tree also ensures that comprehensively you can put up a sample space. So the probability tree is very useful in probability theory because it does this. Another thing the probability tree does is that it shows the probabilities. It shows the probabilities per each outcome. It shows the probabilities per each outcome in the sample space for any given random experiment. Okay, for any given random experiment. And this is unlike the previous theoretical representation of a sample space which had no accommodation whatsoever for this. Okay, so in the theoretical representation of the sample space, there was no accommodation whatsoever for using or assigning probabilities to respective outcomes in the sample space. So if you are using the probability tree, take note, the probability tree is expected to show you the probabilities per each outcome in the sample space for any given random experiment. Now, a third thing that the probability tree does is this. Number 3. The probability tree can be used effectively. It can be used effectively to determine the probability of events or event spaces, just like the theoretical representation. Just like the theoretical representation of sample spaces discussed earlier. Okay? Full stop. Now, so the probability tree can be used effectively to determine the probabilities or the probability of events or event spaces, just like the theoretical representation of sample spaces discussed earlier. Now, why won't you use the probability tree is very obvious. Now, why won't you use it? You should be using the probability tree as an alternative to the theoretical representation for sample spaces, okay? Because, like we have just discussed, it presents a sample space in a more elegant manner, direct manner, and even comprehensive manner. Another advantage is that it shows the probabilities per each outcome in the sample space for any given random experiment. And thirdly, the probability tree can be used effectively to determine the probability of events or event spaces, just like the theoretical representation of sample spaces discussed earlier. So, all these are the advantages of using the probability tree. Now, let's stop here with saying some of these things for probability tree and go straight into a description. Now, before we go into a description of a probability tree, I'm going to tell you to take note of two things. In a probability tree, there is something called a node. There are nodes and branches. Okay, so there are nodes in a probability tree and branches in a probability tree. Now, what will a node do and what will a branch do? A node will just simply be a joining. It is a point in the probability tree from which branches emanate. Okay, so the probability tree begins with a source node. So what we are describing to be a probability tree is a tree or a diagram like this. It comes out from what we can call a source node. You start with a source node. Okay, like I just told you, a node is a point in the tree diagram or the probability tree where branches emanate. So this is a source node, and from this source node you would see two branches or more can come out, so or emanate from the source node. So if this is a source node, this will be a branch and this will be a branch. So this is a branch, this is also a branch. Now take note, the node can be called an end. Okay, so another name for a node is an end. So this can be an end. Now at this point you can form another node, so you can have several nodes in a particular tree. So it can keep coming out, several branches from a node. Several branches from a node can keep coming out for as many nodes and as many branches you want to have in a probability tree. So what we are calling a probability tree is one that has branches and nodes, also called endpoints, okay, or ends. So let us see quickly how to develop probability trees for some of the sample spaces we discussed earlier. Now let's start with a probability tree for a random experiment involving the tossing of one coin. Let's start with one coin. Okay, so for one coin, I'm going to put here one coin. So for one coin, let's see how the probability tree would look like. So tossing one coin once will give us a probability tree like this, where we have a source node from which two branches will emanate. Now take note, if this is your source node, then this will be a branch 1, and this will be branch 2. Now what will branch 1 represent for one coin tossed once? What will branch 2 represent for one coin tossed once? Branch 1 could represent a head and branch 2 could represent a tail. Now at the end of each branch you have to put a summary. In this case head, and in this case tail. Okay, now notice that in the tossing of one coin there are two possibilities in the sample space, a head or a tail. Now what will be the probability of having a head? It will be 1/2. What will be the probability of having a tail? It will be 1/2. Okay, so this is what we talked about in the definition of a probability tree, that it is a diagrammatic ordered representation of all the possible outcomes for any given random experiment with accompanying probabilities for each of the outcomes. So now if you want to put up the probability tree for two coins, so let us put up the probability tree for tossing two coins once. Now what would we have? You will start with a source node. So this is my source node or endpoint, and from this source node will come out this. Now what will come out here are two branches denoting a head and a tail. Now you could make yours a tail and a head however you want it. Now take note, in the tossing of two fair coins once, you don't just have a head and a tail showing up. Now you will take this as a stage. This can be taken as a stage, or this first stage can be considered as one of the coins. Now from this node here, this endpoint here would emanate two nodes, or two branches rather. Two branches could emanate from this. And what would the two branches do? The two branches are to bring up the possibilities you could have. Now, if a head shows up in the first coin, then it is possible that a tail will show up on the second, and that gives us one part. These two branches here will describe one outcome: head, tail. It is also possible that the first coin could show us a head, and the second coin will also show us a head, and that will give us the summary here: head, head. It is possible that the first coin will show us a tail, but the second will show us a head, and that will be head, head, tail, head. Okay? And it is possible that the first coin will show us a tail, and the second coin will also show us a tail on this branch, and that will give us the summary: tail, tail. Now, to each of these outcomes, head, tail, head, tail, head, and tail, tail, will be the corresponding probabilities 1 over 4, 1 over 4, 1 over 4. Answering the question, what is the probability of having the first head, the first coin showing you head, and the second tail? It will be 1 over 4. What is the probability that the first and the two coins will land showing you head, head? It will be 1 over 4. What is the probability that the first coin will show you a tail and the second will show you a head? It will be 1 over 4. Likewise, what is the probability of having two tails? It will be 1 over 4. Now, that is a probability tree for tossing two coins once. What if we toss 3 coins? What if we toss 3 coins? What if we toss 3 coins? 3 fair coins, okay? Now, if we toss 3 fair coins, we would have a probability tree like this. So, we would have the first stage will be for the first coin, okay? So, we call this, let's call this a stage. For 2 coins, there were 2 stages, so let's call this a stage. Now, this is the source node where it all begins, and this will be, you could choose this part to be a head or this branch to be a head, and this will be a tail. Now, at this point, we could bring out another branch. We could bring out another branch that will have endpoints or nodes. Now, this would be this branch. We could call this branch a head, and we could call this branch a tail. You could come here and call another, draw out 2 branches from this other node, and you could call this branch, you could call this branch a head also, and this one a tail. Now, certainly it does not stop here. It won't stop here. This stage is not complete. So let me bring it here. Let me bring this here. Okay. Now, because there are 3 coins involved, you would have 3 stages. So this is a stage 1 for the first coin, stage 2 for the second coin, and we would have a third stage, stage 3 for the third coin. Now, from this node here would emanate 2 other parts. Because why are we having 2 parts at each point? It is simply because for every coin there are 2 sides. Okay, so we are having 2 sides coming out, or 2 parts coming out from every node, because every coin has 2 sides. Every fair coin has 2 sides. Okay, so this will be head, tail. This would also be head, tail. This would also be head, tail from each node to complete the third stage. So this is third stage or stage 3. Okay, so from the last node here we would also have head, tail. Now let us take all the parts one after the other to get summaries. So from the first part, you have head, head, head. Can you now see the order I was talking about? The order diagrammatic representation, or the diagrammatic order representation. So this is now head, head, tail in that order. Head, head, tail for that outcome. This will be head, tail, head. Head, tail, head. This will be head, tail, tail. Head, tail, tail. This will be tail, head, head. Tail, head, head. This will be tail, head, and tail. Tail, head, tail. This will be tail, tail, and head. Tail, tail, and head comes out as a summary. And this will be tail, tail, tail. Tail, tail, tail. Making a total of 8 possible outcomes when 3 coins are tossed once. Now, what will be the accompanying probabilities? All of them, each of these outcomes will have probabilities of 1 over 8. So putting up these gives you what is called the probability tree for this random experiment. Now, let us move on. You could experiment or try your hands on probability trees for 4 coins, 5 coins. You could try them in a similar manner. It may become very tedious to do so, but you will actually get a diagram like this. Okay, so let us look at the probability tree for one die. So when you toss one die once, let's see what the probability tree will be. Tossing one die. Okay, so you end up having a probability tree. Now you can quickly deduce. You will notice that from the source node would emanate 6 branches. Why are we having 6 branches? We are having 6 branches because every fair die has 6 sides. So this branch 1 will cater for the outcome 1, and of course that will be the summary 1. Branch 2 will cater for the outcome 2, and that will give us the summary 2. Branch 3 will take care of the outcome 3, and that will give us the summary 3. Similarly, you would have 4, 5, and 6. Now, these are the outcomes. These are the branches. There are 6 branches because there are 6 sides of a die. Now, this would summarize with probabilities 1/6 for each of these outcomes. 1/6, 1/6, 1/6, 1/6. So, a diagram that shows you a representation, an ordered representation of all the outcomes in a sample space is a probability tree, especially when each outcome has a probability assigned to it. Now, you will notice one demerit or one disadvantage of the probability tree. It becomes tedious to put up a probability tree when the number of die becomes more than 1 or even 2. When the number of coins becomes more than 3 or 4, it becomes tedious to put up a probability tree. So let us do this for two die. Okay, let us just show for a particular part what to do, and you can continue from there. So for 2 dice, let's see, you are going to have from the source node 6 parts emanating 1, 2, 3, 4, 5, and 6. And this will represent the outcome 1, 2, 3, 4, 5. So I'm going to put here 1, 2, 3, 4, 5, and 6. And this will be the source node. Okay? Now, from this source node came out 6 branches because there are 6 sides for any given die. Now, if you bring them out, because there are 2 dies in question, you are going to have stage 1 ending here. So stage 1 will represent the first die. Now, from each of the nodes that end stage 1 will come out 6 branches. 1, 2, 3, 4, 5, and 6. Now, this branch could carry 1, 2, 3, 4, 5, and 6. And you could do the same thing. You have to do the same thing for all of them, all these nodes. You can see how complex it becomes using the probability tree for experiments like this. This will be 1, 2, 3, 4, 5, and 6 for this outcome 6 in the second stage. Now, if you want to summarize, I'm not going to do this because clearly you can see that the spaces available will not be enough to bring out 6 branches from each of these nodes. The one connecting 2, the one connecting 3, 4, 5, 4 and 5. Okay, so let's see how we now summarize. This will be the part 1 with 1, giving you 1, 1 as an outcome. The part 1 and 2, giving you 1, 2 as an outcome. The part 1 and 3, giving you 1, 3. If you continue, you are going to have 1, 4, 1, 5, and 1, 6. If you do the same thing for these ones, you are going to have 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. You are going to have 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6. You are going to have 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, 4, 6. You are going to have 5, 1, 5, 2, 5, 3, 5, 4, 5, 6. You are going to have 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, and 6, 6. Now take note, each of these outcomes will have a probability of 1/36. Now, this is how your probability tree for 2 dice will look like. Okay, so it will display a diagram like this. If you have a wider space, you can try it, and you would assign to each of the outcomes 1/36 as the probability. Okay, so thank you very much for watching this video. You can try your hands on more experiments than the ones we've discussed in this video. Please, thank you very much for watching this video. I'll see you all in a bit. Take note, in our videos on solver series for problems on probability, you would have a lot of problems on probability theory solved there. So watch out for the video on probability discussions, probability solutions. Please watch out for that video. It is very important you watch that video because we are going to be solving so many problems in a series on probability. Thank you very much.